All right, y'all. We're next going to talk about the energy and the components to the energy for the hydrogen atom. So the hydrogen atom has a positively charged nucleus. It has a negatively charged electron. In the simplest model, right, we can think about that electron as orbiting the nucleus. In reality, it's described by a wave function. Of this form. And we know that the electron is assuming a spherical shape around that positively charged nucleus, so that the hydrogen atom is a spherical atom. This, and we won't go over it in this class, but you can take this wave function and you can do a few different types of analysis with it. And one of those analyses is you can look at what is the average radius for the electron. So where on average, how far away from the nucleus is it? So when we take this wave function here, and this is a adjustable parameter that we have for the wave function, this alpha that's here and here in the equation, as alpha gets bigger, the average distance of the electron from the nucleus gets smaller, and so the atom shrinks as alpha gets bigger here. So as we adjust this parameter up and down, we're adjusting the average distance of the electron from the nucleus. All right, so let's talk about the components of the energy that we have here. So one component that we have is the electron has mass and it is moving, so it has kinetic energy. So the electron has kinetic energy. And for historical reasons, this gets written as T11. The other thing that's going on within the hydrogen atom is there's potential energy. And we call that term V11. So that the total energy is T11 plus V11. The T11 is always a positive term. The V11 is always a negative term. And for any stable atom or stable ion, the total energy is always negative. So what we can think about here is the electron adjusts its average orbit until it gets a minimum here. Okay, so when it's really, really far from the nucleus, the T11, the positive term, is small, but the V11 is also small. When it's really close to the nucleus, the V11 is large and negative, but the T11 is large and positive. And so the electron adjusts its orbit, adjusts its movement in here until it gets a minimum for these. I will provide you guys with the actual terms for these. So 1/2 alpha squared and equals minus z alpha. Okay, and this z is going to be the atomic number, which comes from the periodic table. Z equals 1 for hydrogen, but if we wanted to look at something like He plus, like the helium cation, then we would have the Z equals 2 here. So that's an interesting thing to look at. So E for one electron system here in terms of alpha equals 1/2 alpha squared minus 1 times alpha for hydrogen atom, and the 1 electron energy in terms of alpha for the helium plus 1 cation is 1/2 alpha squared minus 2 times alpha for He plus. Okay, so there's a few different ways that you can approach this. You can go and just say start with a small value of alpha. Alpha always has to be positive, but start with a small value like 0.1, 0.2. Put those in and see what different values you get for the total energy. And from that, see where the minimum is. Try to zero in on it. Also, you could do, you could take a derivative of these functions. You take the derivative, you can directly find the minimum of the function. Either one of those would be fine to do this. But the main thing that I would like for you guys to get out of this is to put together, you don't have to do this, well, I may end up asking you to do this for homework, but this is something that's worth you sitting down and doing, is alpha T11, V11, the total energy and doing this for a few different spots in order to find what the minimum energy is, because it's really interesting to see how there's a sweet spot where you get the best balance between the positive T11 and the negative V11. You get the most negative value is what you're looking for. That'll be the stable. That'll give you the stable, the total energy for the stable atom or ion. All right, it gets more complicated here pretty quickly. We can go and now talk about 2 electron atom or ion. We'll talk about 2 electron atom here first. Helium, we got +2 charge in the nucleus. We've got an electron, and we've got another electron here. We saw a couple of the types of energy that this system has already. The electrons here, they have mass and they're moving. It ends up they're moving in the same orbital, so they get 2 T11, so a T11 from each of them. Each of the electrons is independently attracted to the nucleus. And we get a 2 V11, a V11 for each of those guys. And then finally, what makes everything complicated for multi-electron atoms and ions are these types of terms. We go in, and this, what I've marked here in green, we call this guy J11. Okay, and between 2 electrons, there is one interaction that's happening. Electron 1 with electron 2, or electron 2 with electron 1, however you want to think about it, but it's one interaction. So person A, person B, there's one handshake between the two of them. One interaction. Alright, so then the total energy for a 2 electron atom or ion, so E for a 2 electron in terms of alpha, and we got that same type of wave function. Both of them can exist in a 1s orbital. The same wave function that I showed you earlier. So if we go through and work all this out, we get, so it now has 2 electrons, so we double the kinetic energy. So double of 1/2 alpha squared gives me just alpha squared. We double the nuclear attraction, so 2 times Z times alpha. And most important for chemistry here is this final term, 5/8 times alpha. Okay, this one here is that electron-electron repulsion. So T11 equals alpha squared for the system. The V11 equals -2 alpha times Z. And then finally, this last term that we have here, this J11 is equal to 5/8 times alpha. Okay, 0.625, if you wanted to think about it as a decimal. And so then same sort of thing happens that we saw with a 1 electron atom or ion. We go through, for a particular one we set Z, so if we want to do helium atom, Z here would be equal to 2. And so for the helium atom, what we would have, the 2 electron energy for the helium atom, alpha squared minus, so for helium atom that means Z equals 2, so minus 4 alpha plus 5/8 alpha. And so you should be able to do the same thing here again. Alpha value, T11, V11, well, it's for 2, so let's go ahead and say it's for 2, and then J11. Okay, and start at a small value and get larger and larger and larger, and you'll find an optimal, you'll find the most negative energy, and that will be the energy, your calculated energy of your 2 electron atom or ion. Okay, we'll stop there and we'll come back with talking about. Alright, so our question for today is the 1s orbital may be represented by the wave function psi, which is a function of alpha and r, is equal to square root of alpha cubed divided by pi times e raised to the minus alpha r. Okay, if we take this as a wave function, in this case the total energy of a 2 electron atom or ion is given by the following equation. E, for a 2 electron system, its function of alpha is equal to alpha squared minus 2 times Z times alpha plus 5 divided by 8 times alpha. What I'm going to ask you to do is, what is the optimal value of alpha for the lithium plus ion? What is the total energy that is predicted for the lithium plus ion at the optimal value of alpha? Okay, and this Z here, this is the atomic number. Atomic number for lithium is going to be 3, and we would get that from the periodic table.